Okay, so let's continue our conversation about continuity. And this time let's do the exact same problem that we just did, except this time let's show that this function f of x is equal to 1 over x on the same domain, so it's still 0 to infinity. Let's show that that function is continuous at any arbitrary value of a. So the last example that we did for this problem, we did it at a is equal to pi. So we took one specific point and proved continuity at that one point. But now let's do it for any arbitrary value of a on the domain from 0 to infinity. So again, this is going to start out very much like the last problem. We're still going to start, and you always want to start out by just decomposing this term right here, this f of x minus f of a is less than epsilon. You always want to start by decomposing that with these problems. So let's just say f of x minus f of a. Again, this is an absolute value. And just plug in what this is. So this is just, we're using the function 1 over x. This is literally just going to be 1 over x minus 1 over a. Still an absolute value. And then just do some simple algebra for that and get common denominators like we did last time. And you get back to the x minus a absolute value over xa. So again, this is just by definition, this is what you get. Now is the tricky part to this problem. So the last time we solved this problem for a equals pi, we chose an arbitrary delta value that was greater than 0. So we chose 1, and we went through and did all the manipulations and got the delta values that we needed to make this proof work. This time, since we're doing this for an arbitrary value of a, we're going to have to be a little bit more clever. And you know, the initial instinct that you're going to have with these problems is you're going to say, okay, well, let's just make, let me grab my pen again. You would say, okay, well, let's just make x minus a less than a. And again, you can do that. You can typically do that because you're doing this for any arbitrary value of a. So you could literally just say, okay, well, this a is going to equal to delta, and we know that x minus a is less than delta. So that's going to be something you'll commonly see done in textbooks. You'll probably see a lot of examples online where it's done like that. And a lot of times that will work. The problem with this particular problem, though, is that we're dealing with the function 1 over x. And if you remember what 1 over x looks like, it's going to look like this. Hopefully, by the time you're in analysis, you remember what 1 over x looks like. But if not, there it is. And again, we're only focused on this section of the domain. Because again, our domain in this problem is 0 to infinity, so that's all we care about. But what happens as you get infinitely close to 0? As you make those a values smaller and smaller and smaller, and they get closer and closer to 0, this function value blows up. It goes to infinity. And that's going to create problems for you because you're trying to bound this and make it smaller than delta. Well, if you say delta is infinity, that doesn't really get you anywhere. So what you want to do for something like this is you want to make sure that you can never get that close to 0. You never want the value that you're choosing to get too close to 0, because if it does, you blow up to infinity. And so the trick to get around this is to say that x minus a is always less than, we're going to do a over 2. If we do a over 2, that always keeps this value away from 0. Now you could have easily done a over 3, you could have done a over 4. A over 2 is pretty arbitrary. The only reason we're doing a over 2 is because we want to find some term that'll keep this away from blowing up at x equals 0. So you don't want to do this. And then once you get to this point, you're gonna decompose this kind of like we did the other problem. So if x minus a is always less than or equal to a over 2, well then you know that x is always between a over 2 or 3a over 2. And so then if you multiply, if we take this one step further, you would have that a squared over 2 is less than x, which is less than 3a squared over 2. And my apologies, that should be xa. And then again, we're trying to take care, so let me get a highlighter. So the part that I'm highlighting in purple here, this x minus a in parentheses, we have that already bounded. Because again, our definition of continuity, we say that x minus a absolute value is bounded by delta. So our numerator is already bounded. So the only issue that we have to writing this proof is this denominator, this xa term right here. And so by getting this inequality right here, we can bound the denominator to where we can force it to be smaller than a certain value. And so the way you want to do that is you're going to want to choose this section of the inequality. And again, the reason is because x over a, or x times a, the smallest that it can get is a squared over 2 based on this inequality. And again, as the denominator gets small, the entire term value blows up. And so you want to bound this in a way that it can only blow up so much. And so you're going to want to use this side of the inequality. Now, for example, let's say this xa had been the numerator. A hypothetical situation, you had xa in the numerator. In that case, you would want to use this section of the inequality, because then you would want to say that xa, the biggest that it could possibly be, was just 3a squared over 2. But for our example that we're doing here, we're using the denominator. Our xa is in the denominator, and so we want to bound it with this lower inequality. And so now, just like last time, we're basically ready to start writing our proof at this point. You could take the side work one step further, and we might as well go ahead and do that. Actually, let me go ahead and go to the proof, because I've already got the proof right here. So again, like last time, you have 3 different things you want to declare at the beginning of this proof. So again, you always want to say let epsilon be greater than 0. You always want epsilon to be arbitrary, and you always want it to be positive. And so let epsilon be greater than 0 is at the front of all these proofs. Again, x greater than 0, you always need to state, we're proving continuity, and again, continuity is a local property, it's pointwise. So you always want to state that x is inside your domain, and our domain in this problem is 0 to infinity. So if x is greater than 0, x is in your domain. So that takes care of the first 2 statements we made. And then now we're going to say that delta is the minimum of a over 2 and epsilon a squared over 2. Now that might not be clear while we're saying that, so let's go ahead and scroll back up to our side word. So the reason that we're using those 2 values for delta, one of them is right here. So right there we declared that delta is this a over 2, and from that we got all this inequality. And now once we got here at the bottom, let me go ahead and grab another highlighter just to point this out, we got to this right here. And then what you want to do is you want to take this term right here, this a squared over 2, and you want to plug that in for xa, because that's the absolute smallest that can ever be. So then you get this x minus a absolute value over a squared over 2. And again, this is the statement we're making right here. We're making the statement that f of x minus f in absolute values is equal to this. Except now we have inequalities. We say it's always less than that. And we want to say that this is less than epsilon. So now if you move this a squared over 2 over, that's how you can get this. So this would be your second value of delta right here. So that's how you get your 2 values of delta. One is what you're declaring at the very beginning, and then the other one is what you solve for with this inequality. So now if we go back down to our proof, that should help explain why our proof is the way it is. So again, you always want to state let epsilon be greater than 0, x is in our domain, and then we're going to state our 2 delta values. And we're going to say that delta is the minimum of those 2. So then you just have to basically write out the definition of continuity. So then we're going to say that our absolute value of x minus a is less than delta. Again, that's the definition of continuity. And if that is true, then our f of x minus f of a in absolute values is equal to x minus a in absolute value divided by xa. And this part right here is by definition. If you plug in 1 over x, you plug in f of x and f of a into that, you get 1 over x minus 1 over a in absolute values. Solve for a common denominator, and you get this term right here. So that's by definition. This is by the first assumption that we just made. So we chose the a over 2 to be our delta value. And from that, we got the a squared over 2 value, and we plugged that in the denominator. So this right here, this section right here, is the side work that we just did. And then, like I was just explaining, how you solve for the second delta term, that is this right here. So now we can say all of this is less than epsilon, but that's only if you use this second delta term. So hopefully we broke it down in a way that this proof makes sense, and you'll be able to duplicate this proof in other problems. And once you're able to do so and you write out this nice little proof here, Always make sure that you write a big fancy box to make it look like you did a really difficult proof. And that's it.